Okay. Professor Santosh Nagarakatte, thank you very
Hello.
much for doing this. I first want to just get you to introduce yourself and explain your role as the Undergraduate Director for the Department of Computer Science here.
Okay, so you all know me. I'm Santosh Nagarakatte. I'm a professor in the Computer Science Department and currently serve as the Undergraduate Program Director. So I grew up in India. I loved math during my childhood. So computer science was the closest I could get to math. So I did a undergraduate degree in computer science. And then I had a small startup after my undergrad, and then research was what tickled my brain. So did a PhD at University of Pennsylvania, and I enjoyed my PhD so much that I wanted to be a PhD student throughout my life, albeit with a better pay. So that's why I decided to become a professor. And I joined Rutgers in 2012. So this is my 14th year here at Rutgers. Yeah, so it's been an interesting journey. For the last 6 years, I've been serving as the undergraduate program director. So you may be wondering, how does the undergraduate program here work, right?
Yeah.
So first thing is your curriculum needs to be updated, refreshed, and made sure you have classes to attend. So one of my goals as undergraduate director is to make sure sufficient CS classes are all scheduled so that all our students, we have 6,000 students interested in CS major or a minor across 4 years. We are graduating 1,024 CS majors this year. So all those students need classes. The second thing is we need to ensure we need to have new classes. This is the age of AI, someone wants to build a LLM, they need to have classes to learn how to build them. So someone wants to learn cryptography, so they need to have classes to learn about cryptography. So these are all the new courses that we need to create. So as undergraduate director, I oversee. This is the curriculum design part of it. The second part is all your degrees need to be certified. You're graduating with a honors. You're graduating with a BS with the highest honors. So all those are certified by me, overseen by me, done by my admins. And then you have recruitment. You need to recruit new kids to come to Rutgers and join CS. You see me in admitted student open house, major minor fairs. These are the few things I also oversee. The last thing, I also do a lot of outreach. So we are all privileged. So we know why we should pursue CS. But it also happens that we have a lot of kids who still think CS is being in the basement and typing some code. But CS is much, much more beyond it. This is why LLMs are not going to eat CS. So I do a lot of outreach. So one such outreach that I've done, which I'm proud of, having been involved in the EOF program here at Rutgers, which is financially underprivileged groups. There's state funding that comes into Rutgers, and they get placed with an advisor, and they major in various things. So Rutgers and various other public universities in New Jersey have such a program. And I've been what I'd noticed was not many CS majors from EOF were present 6 years ago. So we had I had a talk with Michelle, Shostak. She runs the program here at Rutgers, and now the number of EOF students have increased. So these are some of but I can keep going.
So your main role is you talk to a lot of students, you do a lot of outreach, and you also are in charge of course curriculum.
Yes, and also advising, few other things, and we are all humans. Students don't agree with their instructors, they have disputes, and I am the overseer of disputes, ranging from grade appeals to this instructor is not providing me a makeup. So
I'm sure students flood your inbox every day.
Yeah,
right?
So I get on a busy day 600 emails a day.
Wow. How many do you get through?
This is my one of the things I've done it as a policy through my 6 years as undergraduate director. I respond to all email within 2 hours.
Wow. Oh my gosh.
At least it's not at night. Cut me some slack. If you send me any email during the business hours, I respond to you in 2 hours.
Wow.
And because it may not be important to me. There are other students, their problem is so important, and their mental health, their benefits, their progress all depend on receiving that email.
Yeah.
So I empathize with a lot of students. So sometimes I don't agree with whatever they are requesting, but still they'll get a response from me.
Wow. That's great. Thank you so much. I want to kind of go into a little bit of your research. You said after undergrad you were in a startup and you really felt that you wanted to go into do a PhD and do research. So how did you sort of figure out that research was for you? And I know Your research is like in sort of numerical methods, and I believe you didn't really have a background in numerical methods before you started. So how did you figure out that that's what you wanted to pursue?
Okay.
And yeah, you can also explain a little bit of your research as well.
Okay, so I do a lot of things.
Yeah.
Numerical methods is what I do right now. During my undergrad, I was interested in networking. This was the age, like I'm a dinosaur in the room, right? So I'm old. So I used to work on advanced distance vector protocols for wireless networks. So this was like way early in the 2000s. And this is like you have two mobile hosts, they want to exchange messages and they don't even have a base tower. Like you don't have a, and then how do they exchange messages? So there are the hopping protocols, and that's what I worked on.
Okay.
And networking was the thing. And then I was designing easier methods to specify these networking protocols. And that's when I realized, oh, there are domain specific languages and you write compilers to express them. So I got interested in compilers. And I was building, like as part of the mini projects that I was doing, I was putting together machines, building compilers. Then I know, oh, you need to actually make the hardware faster. Like you can build like you can have a fancy house, but if it does not have all the modern amenities, right, modern plumbing, your house is it's a fancy stone.
Yeah.
So it's the modern amenities that makes the house habitable, right? Similarly, like it's the hardware that makes the system go faster. So I was interested in building hardware. So one of the cool results that happened in during my undergraduate days was I grew up in India. So there, the IIT Kanpur had this cool result called primality testing is in polynomial time, and that was mind blowing to me. So I spent 3 years of my undergrad doing research on number theory,
Wow.
apart from all the projects. And then I realized, like, maybe I'm not good in number theory. I will never produce anything. But the fact that I pushed myself and read, I valued, like, what is it to produce a new piece of knowledge. So there's a professor, Matthew Might. He used to be a professor at Utah. Now he leads precision medicine in Alabama. So he has a blog post. Like, I will share the links to you later on so that you can share it with others. So let's say like one concentric circle is the entire amount of human knowledge. When you do research, you are pushing the boundary by a very tiny nudge. And when you do undergraduate, you have when you complete your undergraduate degree, you have a small concentric circle, which is a very small piece of knowledge. And the part of doing research is pushing this boundary to the surface and making a tiny nudge there.
Yeah.
And there is like joy in doing it. So this is what excited me about research.
I see.
So that's why I pursued it. And so initially I started in networking, then number theory for a while, and then compilers. And during my hardware, there was the story about like, how do you build hardware? Like for example, today, why is your hardware fast, right? So you have a program, you write a sequential program, right? It's a total order. You might have taken a discrete structures course. What is a total order? Every instructions are ordered. It's sequential. But what does your hardware do? It takes this total order and identifies what can be executed in parallel by looking at true dependencies. So it creates a partial order out of a total order, and then it executes them whenever the instructions are ready. This is called as out of order execution.
I see.
And this is all modern processors do this. And this is why you don't have to write faster programs, your program was getting faster.
Wow.
But in 2005, what happened was like this out of order execution needed a lot of other extra structures. They started consuming a lot of power, and you didn't have energy to cool them. Like now, like you would have to plunge them in liquid nitrogen to cool them, and that's not fun, right? So one of the debates at that point in time is, can we like in order processor just execute as you said, and out of order is doing all this fancy partial order extraction, fancy parallelism in the hardware. So can we somehow bridge the gap, performance gap between in order and out of order processor? This was the first problem that I attacked for my PhD. So how do I take a in order processor, add small structures, and almost get the power of performance of out of order processor?
Wow.
So I built a cool idea. This was with my then advisor Amir Roth, and we called it in order continual flow pipeline. So what happens is, imagine you have an in order processor. Your processor just executes things in the order it was required. And now why can't you execute other instructions? You have an instruction that misses in the cache, and you have to go to memory. It takes a long time to go to memory. So in order processor typically would stall, wait till the request comes back. My idea was take the the instruction that is missing and drain it into a small buffer called, let me call it the slice buffer. And the cuteness of the idea is like you have a miss and there are other instructions that are depending on it.
I see.
You grab them and also put it in this buffer. So now what happens is this slice is self-contained. Once the value comes back, you can just like fill it in. It's all self-contained.
I see.
And then you can re-inject it back and execute it.
Wow.
And what we showed is we can almost bridge 90% of the performance of out-of-order processor by just having this extra buffer and this technique. We call it in-order continual flow pipeline. This was my HPCA 2009 paper, and this was recognized as the top picks of computer architecture in 2010. That's like the best architecture paper of the entire year. So that was my start. And then I wanted to explore hardware. Then what happened was like to get anything in hardware to be built, you need to convince Intel, AMD or NVIDIA to build it. How can I build it here? So this is where I gravitated more towards like something I can build. I don't have to wait for Intel to put something into their chips, right? So it took a lot of time to do that. So one of the issues, like I had written a lot of C code at that point in time, and I would write, you would have a program, a small error, a memory safety error would be a security vulnerability. And like around that time, there was a configure Stuxnet, a lot of other worms happening, small errors resulting in catastrophic security vulnerabilities. So I said, like, this is an easy problem to fix. Like, rather than having band-aid solutions, we can have a comprehensive solution. So in my PhD, I proposed what is the most comprehensive method to prevent all memory safety errors, buffer overflows and use after free errors. So I called it soft bound and sets. I proposed a collection of tools, and to reduce the overhead, I also built hardware extensions. So Intel at the same point in time was excited about this idea. They got an army of engineers involved in it. So they proposed an ISA extension called memory protection extensions, which was exactly inspired by my research work. And in fact, like I have Intel compiler team telling me like they use my PLDI paper to implement their own pointer checker internally.
That's amazing. Wow.
So that was my research. And now like effectively what I said is to make a program safe, you take a compiler and do a compiler instrumentation. Now how do you check the correctness of this compiler instrumentation? So at the end of my PhD, I wanted to make compiler verification. Compiler's correct.
I see.
So to do that, like I wrote the entire compiler with my collaborators in a proof assistant.
And for those who don't know, can you briefly explain just what a compiler does?
A compiler is like, okay, I'm speaking a language, right? Like you are understanding it because you understand English. But your hardware only understands zeros and ones. But now you have a programming language, let's say C, Java. It needs to be understood by your hardware, which is converted into zeros and ones. So a compiler takes your source language and converts them into zeros and ones that the hardware understands.
Okay.
So it lowers all the abstractions. So you would think, oh, it's just another translator, right? But that's what gives you performance. And even 2% performance. Imagine like all these hyperscalers are spending $100 million on just one training. You improve it by 2%, like that's $2 million saved.
The faster you can translate, the faster the performance.
But these compilers are beasts. Like look at like the modern compilers. You might have heard of GCC.
Yes.
Or LLVM. Almost Apple, Google, almost everyone uses it. It's like 10 million lines of source code.
Wow.
And there are like thousands of engineers, let's say 20,000 engineers making changes to them.
Yeah.
How do you ensure these compilers are correct?
Yeah.
So one way to do, since I was fascinated by math, so there are theorem provers available. So one such theorem prover is Rock. Now there is a lot of interest in Lean as a theorem prover. So I said, like, why don't you write your software not in VS Code, but in a theorem prover? And it's a lot of work. At that point in time, we showed it could be done. And the memory safety transformation that I did, I showed it to be correct.
So this theorem prover, it basically takes your code and it verifies if it's
So you write proofs, and then there is this beautiful result called Curry-Howard isomorphism. Like there's a correspondence between types and proofs and programs and propositions. So proofs and propositions and types and programs. There's a one-to-one correspondence between. This is a beautiful result in logic.
I see.
So these theorem provers have a dependent type theory. You write in them. You write like programs with proofs, and you go ahead with it.
I see.
Okay.
Okay. Wow, that's
So
really
so
cool.
then after coming here, like what we essentially did was like, okay, I wanted to make writing such large mainstream software correct.
I see.
When I started at Rutgers, I wanted programmers, professionals who don't have a PhD to write correct compilers.
I see.
So that was the first area that I explored on with my student, like who's an instructor here, David Menendez. We were one of the co-developers of Alive, automatic LLVM instruction combined verifier, which showed compiler optimizations correct, and now it's used by around 16 companies.
Wow.
Every day, and like new optimizations are checked every day.
And in the interest of time, I actually kind of want to move it around, but it's very cool that you were able to sort of experiment with so many different things in your PhD. Like you went from networking to hardware. And so I kind of want to have you list sort of common paths that students take after graduation. I know you interact with hundreds of students on the daily, as you've explained. And also sort of explain how students can figure out what paths are right for them and how they can get ahead.
So awesome. So sometimes people think like, oh, the only thing you do is a programmer, right?
Yes, I've heard that many times.
So with a CS degree, like a typical path is you could be a front-end app developer.
Okay.
A lot of students do that. Like it's a good company. Like it's a good initiative, primarily because this is the user-facing aspect, right? Like you develop a new software, but like no one is going to get into the terminal and type things, right? Like you need a good UI, good interface. So front-end design is a good thing, and a lot of developers got hired for good front-end designs. So that's one aspect of it. Like, and some of these technologies for front-end keep changing, so you need to be up to date.
What are sort of the main ones that you have to know for front-end?
Yeah, apart from front-end, like you do the architecture, like you are an architect, like you want to build the next generation Netflix, right? So how would you stream millions of movies simultaneously? So you have to be careful about it. How do you go about doing it?
Yeah.
So you need to design the architecture. What does scalability mean? So the new word is microservices, right? So you can have like, you don't have to buy like millions of machines. You just rent like few machines, and you have your services which are immediately scalable. So you would be an architect for such a scaling thing. And then you're a back-end designer. Now you have a server which you are processing billions of requests coming from everyone. How do you design a back-end so that can scale? And then there are platform designers. Like you are, like if you are at Google, like there are core services used by everyone, like Bigtable, MapReduce frameworks. These are the platform designers, like core compilers, verifiers, like the operating system designers.
So
these are,
they create sort of like, can you give an example? Like what is Bigtable? What is, for people that don't know, MapReduce?
So I think like you want to learn, like let's say like you have 1 terabytes of data coming from an NFL match. You want to analyze every video of it, like, and you want to quickly learn like interesting insights from it, right? So what do? So you have a distributed system with millions of nodes, like, and they all are going to run the same program on each of them, and they're going to produce certain values, and you need to aggregate them and filter them out and generate some meaningful insight. A framework to do this is a MapReduce framework.
Okay.
It's basically a for all applied to everything with a filter at the end.
And this is maintained by platform engineers, you said?
Yeah, these are developed by platform engineers. Like Hadoop, like Google has its own MapReduce. Hadoop is common open source Apache framework. So similarly, there is now with AI, like Spark is one such framework that is commonly popular. So Databricks is a company which develops these platforms.
I see.
So the platform design, like generating core services that is used by everyone. So this is another. But beyond that, like people are like, when you build a large company, right? When you're building a database, so identifying what are the requirements. So you need to have like what are the requirements of your customer? Like you're an insurance company, you need to identify what are the requirements of your customer, so that you can have a spec for the requirements, and so that your engineers can translate into. Now, even those professionals need a CS degree, because if you don't know how to translate requirements into a spec, like you can't even implement the system.
I see. Yeah.
So another class of engineers that are like commonly used are like software design engineers in tests. They develop like various kinds of tests: unit tests, integration tests, and platform integration tests, and various other things. So now some of these jobs are getting automated with the use of tools, but these are all the flavors of jobs.
I see.
And apart from it, like if you work for Roblox, right? So you want to design narratives of stories. like you want to design games. So you want to have like a very interesting creative story lined with the actual game engine. So that requires a lot of work. So even those are like creative areas that you can work on.
Are there sort of non-coding roles that are also?
Yeah, so like if you work at a new, let's say you are a computer scientist hired at New York Times. So you have tons and tons of data. You want to filter them very quickly. So you need to have a CS degree so that you can do efficient filtering, efficient like analysis of data. So is this like whatever like if you go to Ivy schools, you get better jobs. To make a statement, you need to analyze a lot of data and then produce statistically meaningful correlations, right? So without a CS degree, it will be pretty hard.
I see. So really a lot of different roles that require CS degrees.
And we all work in government, like government provides you services. There are a lot of engineers employed, CS professionals employed by like local governments, NGOs and governments, and also like technology policy is an interesting issue. So like all the media companies are getting you hooked up on digital platforms, right? Like how do you get what is an appropriate policy? Now you're going to create a law, you need to have an appropriate policy for.
I see, yeah. So there's a lot of interesting stuff you can do.
Yeah, so I think like this is what I'm, again, I'm a CS professor, yes, advocating for CS, right? My opinions are biased, but I think CS is like the key critical thinking skills that is required for the current digital economy. Like CS for science, CS for like robotics, CS for medicine. So I would say like CS is the core backbone. So instead of the hype that you hear otherwise.
So with each of those things you mentioned, I mean, of course, now that we know you can do so many things with the CS degree, how do you sort of figure out what's for you, just as sort of you did when you were in your undergrad and your PhD?
So that's a very interesting question, right? Like most of the time, like there are a lot of things you want to do, and to have a flair for it, like you need to experiment. If you don't even try, you don't know what is for you, right? Like for example, you're a Rutgers undergraduate. Like you wouldn't even know, like, oh, there are, you are interested in security unless you actually try it out. So there is a USACS, which is a security club, like involve with them, participate in certain hackathons. Like, and when you participate, if you're a passive participant, right, you just attend 1 or 2 sessions and then, oh, no, it's not my cup of tea, like then you don't even like got a hang of it. So I would say like explore it for 1 term, like participate in some hackathons, solve some things, and then like sometimes you it just tickles your brain in the right way. Oh, this is what I want to spend, man, like nothing else. And but sometimes, oh, like maybe it's not my cup of tea. You move on.
What are some ways you can like sort of find new things that exist that you might not even know you could do with your CS?
So one of the things I did is like during my undergrad days, I made it a habit, because when you make something a habit, it persists. So every day I would write, like develop some new algorithm. Like I would code up like something, I have a problem that I want to solve. Like there is a Olympiad programming contest problem. So I would pick up one problem and every day like I will try to code it up. So 1 hour a day. And I would do it, even now I do it like every day. Like so it tickles my brain, like just to forces me to think differently. Like otherwise life happens, you will get subsumed in it. So I think you want to try it out. So concretely try something. So it may be app development. Try out like, oh, you want to learn React Native. So wait, like have a regular schedule. This month I'm going to develop a new app using React Native frameworks. And one of the things you should learn is like just doing it for the sake of doing is not useful. You should have a deliverable. Like if you just don't show any output, like I tried, but like there's no output to show for, like no one will give you credit.
I see.
So you should have force yourself to have an output that is useful to someone.
So let's say like a student is interested in some specific field. How can they like maybe even leverage AI tools to say maybe figure out, like, 'cause let's say they're interested in a certain thing and they're like, what careers exist in this and like what projects can I create? How can they leverage AI tools to figure out what to build and where to go once they have?
So figuring out AI, like sometimes like AI tools. What is an AI tool, right? Like it's a pattern recognition engine. Like with LLMs are next token predictors.
Yeah.
And it's just like trained over large corpus of data. So then what happens is like you get the is mediocrity the best you can use for advice? Like sometimes like if you take out the average and then choose like the average of it, like it may not be the best.
I see.
So if you don't know anything, AI tools may be a good start, but like talk to a faculty member. Like you take like I want to do a cool project. Like what? Or do you have any suggestions?
Maybe like a full stack web app or something like that.
Yeah, sure. Is there an interesting? I think like you guys participated in Project Showcase like few days ago, right? Like so something like you are troubled by, right? Like Rutgers buses like are never on time. The main app is so frustrating. Yeah. Why is it frustrating? Why don't these developers hired by Rutgers don't do a good job? So you get a first-hand experience of like let me try to build it, and then you will appreciate what are the challenges. So data sometimes is not curated, like there's a lot of noisy data, and dealing with noisy data is a hard thing. Yeah. So these are some things to start with.
Okay, so like finding a problem that you think you kind of exist in your life and trying to solve it.
Yeah, so I would suggest like you have 8 terms, 8 semesters for your undergraduate degree. Like if you do a 4-year degree, like every term like you would have a project that you would show for, apart from your core curriculum.
That's a good goal. I also kind of want to talk to you a little bit about the academic side. Considering you teach computer architecture, the jump from data structures to computer architecture is sort of notoriously known as being quite large. And I feel like a lot of students, myself included, will sometimes look at lecture slides and look at lecture material and feel like they understand it, but then get to the exam and realize they really don't. So how can students, number one, assess that they really understand the core material of the class? And also, how can they sort of learn the material as effectively as possible to really gain a true understanding of what they're learning?
Okay, so this is I may have a contrarian opinion on it. Like I think learning anything requires patience. Yeah, but in an age where everyone is like wants to have an Instagram soundbite, right? Like everything needs to be like in 2 minutes,
instant, yeah.
Short size bites. It's sometimes hard. I understand the frustration, and I think learning anything deeply requires investment in time. So go to the lectures. Like I think there is a tendency among many students, like it's not important to go to the lectures. Like some people are like gifted orators, they teach very well. Some people like they're trying to do their best, but like it may not be aligning with your style of narration, but still the fact that you are there in the lecture trying to pay attention forces your brain to think.
Yeah.
Okay, so that's the first thing. Go as much as possible, like you don't want to miss classes, you want to attend classes. Second, like reading lecture slides is not substitute for learning. So there is a misconception among a lot of students that, oh, I can pass a course by just like going over the slides. They have to read the textbook. Like okay. If you take CS211 with me, if you don't read the textbook, you are not passing this course, man. That's the first. So I think you need to read the textbook. And sometimes like there are things like which you understood like from in the lecture, you can skim through it, but you need to read at least do the assignments in the textbook.
Do you think like reading the textbook before the class or after the class is?
It depends on you. Like I think if you have a good instructor, reading it after the class is much more beneficial, because like the instructor would have summarized you, given you all the beacons that you need to focus on. So at least for my lecture, if you're reading it before the class, like man, my lecture would be like cakewalk for you. But if you're at least like read it after my lecture, I use Computer Systems by Randy Bryant, and that's like a 1,000-page textbook, and each chapter is like 200 pages. But my lecture is like on a particular unit would be like five lectures on a particular unit. You read it after the lecture, like those 200 pages, you can do it in like few hours.
Let's say you're like reading a textbook and you sort of get stuck on a specific parts and you kind of just can't figure it out.
So that's why you have Canvas and Piazza, right? Like you should post your question, and this is another trend that has kind of deteriorated at Rutgers and most universities in the US, right? People would show up for office hours. No, I think like my office hours would be jam-packed like 10 years ago. Now hardly 1 or 2 people show up.
Wow, that's
like there are like these usual suspects who show up, but like people like unless it's an exam, you have a midterm or a final next week, no one shows up. So I think use your resources. Like at times like there's a crowd, but learning happens with your peers.
Yeah.
So the last thing I would emphasize, you asked me like how do you know you have learned it? Like Richard Feynman had a fantastic quote: knowing the name of something is useless. I can use fancy jargon, right? Caches, MCP servers, blah, 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 but it's useless. it's just like you can call me Santosh, Hassan, Jamie, or whatever, right? So like they don't mean anything.
Yeah.
You should understand the principle.
Okay.
So best way to learn anything is to teach.
Okay.
So find your friend who's lazy enough, teach him. That's, if you can do that, you
Then you
attain
understand
mastery.
it. Okay. Yeah.
So, and your friend will say, man, why are you such a bad teacher?
So you think if you can explain it to like say anybody who doesn't even know anything about the concept, then that's
Like
when
you want to teach caches to your friend. Like,
Yeah.
why do you need a cache? And like, what is the best example to give a cache? So this is the example I give. Like, you have a bookshelf with a space for 2 books, and you need to read 6 subjects. And where do you get the books? You go to the library, and library is 50 miles away. You are a commuter student at Rutgers. What do? For every book, now I'm going to read Compark. I go to the library, get a Compark book, travel 100 miles, and come back, and then finish it, and then go back. What is caching? When you go to get the Compark book, you also get the Algos book, and you come back, you put both of them in your stack, and you read both of them, and then you amortize the cost of going to the library.
Yeah.
Right? So something that seems natural. Like, I think there is a beautiful insight behind every idea in computer science. So you get the essence of it. You don't have to remember like all the jargon. Okay, what is associativity? The number of slots in your bookshelf.
Yeah.
But like people will forget. Like if you just say associativity, cache size, line size, blah blah blah, all those will be forgotten. But if you understand the essence of it, it will stay with you forever.
Okay. Yeah. That's
So
great.
I think like my essence is like, this is what I tell my students in TS 211. You want to learn, you should learn it like swimming and driving. So you learn it once, it stays with you forever. So it doesn't matter which car you ride, you learn driving, right?
Yeah.
So similarly, like once you have learned it, it stays with you forever.
Yeah.
So you don't have to learn everything, but whatever you learn, make sure you learn it such that it stays with you forever.
And make sure you can explain it to others.
Yeah.
Okay. Wow, that's great. I also wanted to talk to you a little bit about AI usage. I know that it's sort of picked up a lot, and especially with like assignments. I'm wondering, as an educator, how you view your assignments, and like how you want students, or what you want students to get out of your assignments, and also how you sort of think AI can be used as a learning tool, but also as just a tool in general to use in different contexts.
So I think like we are in very interesting times, man. I think like it's like being kid in a candy store. So for example, like if you told me like people would answer questions so fluently for anything 15 years ago, I would say, no, that's not going to happen.
Yeah.
I think this is a remarkable feat, like what these LLMs are able to do, right? They are able to answer questions in a manner like which is succinct and clear.
Yeah.
So it also made like one of the things we used to say in computer science is like, oh, knowing a particular language is not important. Like it's your ideas. And but people would say, oh, I'm an expert in Java, I'm an expert in C, I'm an expert in Rust. And what these LLMs have shown is like,
it doesn't really matter.
the languages actually don't matter. It's
Yeah.
your ideas. So these are like exciting times. So as an educator, like I'm also like, my problem is confounded by 2 things, right? So if you give let's say 211 assignments, right? I set these assignments new every time. If they just take the PDF and give it to an LLM, it will generate a working C implementation. And you can submit it, it passes all the test cases. So what have you learned in this exercise?
Pretty much nothing.
Yeah, precisely. So sometimes like you can read like a lot of swimming manuals. I can teach you, oh, this is the butterfly stroke. Like you need to move your arms this way. Unless you go to the pool and try it, like you'll never learn it. So now how do you convince students? You have to try it out yourself. Like just don't give it to LLMs. So this is a challenge in education. And now like there are a lot of kids like who have poor time management abilities, and they eventually like, okay, assignment is due tomorrow, like they'll use it and submit it. We can do pairwise plagiarism checks and like, oh, you copied and other things, but that's being a cop at the end, right? Like that. But for me, like I want the student to learn. It's like, what incentive structure can I provide so that students are forced to learn? This is a difficult challenge that everyone is grappling with. Like as an educator, how do you make students to learn the core concepts? Sometimes whatever you think is not interesting will come and haunt you later in life. So it's like, how do I force you to learn? and sometimes experience is a good educator, right? Like the reason I'm saying this is because I have I've been an educator for 20 years, so I know like this is important. Students at times like, why are you making me learn it? Like now I get thank you emails. Man, I took your computer science class 10 years ago. That was I found it hard, but now like I realize how useful it is.
Do you have any ideas of how like you can maybe force people to learn even?
Yeah. So the way that the model, I taught a graduate compilers course last fall. I wanted students to build an end-to-end compiler from C-like language to x86, and it should run on their machine. It would typically take 3 terms for students to build that earlier.
Wow.
Before AI. So I made my students, you can use whatever AI tool you at your disposal, but you have to get the program to be entire project done. And it made students super productive. Almost all the students got their projects working.
Wow.
And then I also wanted to ensure they learned the actual principles. So I had a final exam which had equal weightage, where they tested, like I was building the entire project with them, right? I would have snippets. If they had not thought through carefully, if they just prompted and given the PDF to Cloud Code and got the output, they would not be able to understand it.
So you think like leveraging, I guess, perhaps like bigger projects, but also like exams that make sure.
Yeah, I think like more in-person Viva voices and exams may become more crucial to just like force students to learn.
I see. Yeah.
So my colleague Rich Martin has a nice term for this: cognitive surrender. So one of the things we worry about is will students surrender their ability to think, and this is where like with a tool which is like pretty excellent, right? There'll be.
I've certainly been in those situations. Yeah, like you'll get output and you can just plop it into VS Code and you're like, okay, I don't have to think about it. But
so the other thing to keep in mind is like it's not when you build software, right? It's not you're not doing it one time, right? Like there are a few things you do it once and then no one cares about the code. In those cases, white coding is like useful. But if you're building platforms, right, it needs to be maintained for like 15 years.
Yeah.
So how do you write maintainable software? Like I don't know whether you looked at like the code generated by these vibe coded tools. They are incomprehensible at best.
So do you think it's still important that students use these tools because they are of course being adopted in industry and I believe research as well?
Again, unlike some of my colleagues in humanities, I have a contrarian viewpoint. Like again, I said like students should embrace these tools. For example, many of the Fortune 500 companies, when they interview you, they no longer ask you to ask questions from lead code. They ask you to build a project. They'll give you a specified amount of time. Use whatever tool at your disposal. Get the project done.
I see.
So in those cases, like if you're not like competent with these tools, like you may probably able to do it in like the time specified, but you will be. It's like writing no one writes assembly code anymore, right? Like you rely on compilers.
Yeah.
So I think like maybe like different techniques. How do you validate the result of a code? How do you think about correctness of code? How do you think about design becomes more important than just the plain code that is.
I see. And do you think AI can also be like a supplemental tool in terms of helping you learn? Or
so I think like it's typically how would like people find resources, right? Google was an exemplar in this. Like you would search, it would show up links and resources. And then there was the age of Stack Overflow where like there was a question, Google would index some Stack Overflow question, you would read from it, it would work. So I think these AI tools, like for example, like if you have a Copilot extension on your VS Code, it will fix it. If you have a compilation error, it will immediately show how to fix it. What are possible fixes? What are the ramifications? That's a very good learning curve. This is why, as a computer scientist, this is being a kid in a candy store, right? Like it's like the opportunities are limitless.
I see.
But I think with any tool, right, you have to be careful. Overusing it can have ramifications.
Yeah, like, and could lead to cognitive surrender.
Yeah, precisely.
So just in closing, I wanted to sort of ask you, what do you think will be something that students will need to know, and is like a piece of advice that students will need to know that will sort of last into the future, maybe 5 years from now?
So I think like sometimes like, okay, so problem solving skills, abstractions, they will stay with you forever. This is the essence of a CS degree. It's not the particular languages that you learn, particular assignments that you solve. You learn something, learn as if like it will stay with you forever. And the other thing is about like Rutgers is an R1 institute, a research heavy institute. You should engage in research.
research?
So just cold mailing faculty members saying that, oh, I want to do research. Like, take their courses, read the research papers, and ask interesting questions and involve yourself. Like, doing anything requires time, like a commitment of at least 10 hours per week, and do something, even if that's not what you are interested in. Like, say, like, you're not interested in AI in the rest of your life, but like just learning, like building an LLM all by yourself, so that you can write GPT-2. And Rutgers University has a nice YouTube video on how to build a GPT-2 all from scratch. So build it so that you learn it, and now you don't have to work on it for the rest of your life. Your university education setting is a good skill. So the skill that will be important for you for your rest of your career is, CS is not about, I have learned this knowledge, right? It's this curiosity to learn, this desire to learn. And my mentors instilled in me, there is no end to learning attitude. Like, I know a few things, I'm an expert in some topics, but I don't know a lot of things. I'm curious to learn. So keep an open mind, and in any profession you will survive.
Awesome. Thank you so much.
Awesome.